Okay, so welcome to my series of video on statistics. And in this particular video, I'm going to explain the issue of simple linear regression. So when I talk about simple linear regression, I'm going to talk about regression that involves two variables. Okay, now I would like you to comment, share, like, and more importantly, subscribe to this channel. Now, when we talk about regression, regression comes from the word regret. So when we talk about regression, regression comes from the word regret. And regret simply means to go back. So if somebody says that I have regretted something, the person means, or the person wants to say that he or she wishes that she could go back. Okay. Now, this simply means that when we talk about regression, it means that there is a root cause or there is a going back to find out what caused it. All right. So in simple terms, regression is a word that was coined out of regret, all right, to show that one variable causes the other, or one variable goes back to another. Okay. So here, when we talk about regression, unlike correlation, regression is a cause and effect relationship between two variables. Regression is a cause and effect relationship between two variables. Now, if regression is a cause and effect relationship between two variables, it means that there will be the causer and there will be the cause. Okay, so it means that there will be a variable that is being caused by the other, and there will be a variable that causes the other, all right? So the variable that is being caused by the other, or the variable that is being determined by the other, is called the dependent variable, the dependent variable. And on the other hand, the variable that causes the other, or the variable that determines the other one, is called the independent variable, okay? Now, this is a simple regression model. So regression can be depicted on a graph. So we can depict regression on a graph like this. So we have y, which is the dependent variable, and let's say we have x, which is the independent variable. All right, so assuming this is the relationship, it means that when we put in a value of x in this equation, okay, remember every straight line is an equation, okay? So when we put the values of x in this equation or this straight line, it can help you predict, or it can cause y, or it can determine y, okay? Now in this line, we have the value of y when x is 0, and that is the y-intercept, okay? And of course, this line also has a slope, okay? So the slope is simply changing y as a result of what's changing x, that is the slope. So in other words, in every regression model, there is a dependent variable, which is the y. There is the y-intercept, which is the beta naught. There is the x variable, which is the independent variable. Then there is the beta 1, which is the slope of the regression equation, the slope of the regression equation, all right? The slope of the regression equation, that's changing y as a result of changing x. That is the slope. And of course, our regression equations cannot perfectly predict y, okay? So definitely there will always be a deviation of predicted y from the actual y, all right? And that is shown in the error term here. Now, for us to go into the detail of regression, we must know that regression is based on certain assumptions. The first assumption is that the individual value of the error terms are statistically independent of one another. And these values represent a random sample from the population of possible error values at each level of x. So here, what we are saying is that the error values or the error term in a regression equation, they should not be related. They should be independent of each other. And in statistics, the situation where the error terms are independent of each other is called homoscedasticity. Homoscedasticity, all right? The second assumption is that for a given value of x, there can exist many values of y, and therefore many values of the error term. All right. But in all this situation, we are saying that all the error terms put together, the error term, if you are drawing a distribution for the error term must be normally distributed. And that is also another assumption of regression. The third assumption is that the distribution of possible error values have equal variances for all values of x. Okay, so let me make this correction. Issue 1 was actually autocorrelation, okay, or serial correlation. So issue 1, or the first assumption, is that the error terms must not be related to each other. That is rather called, when they are related to each other, it's called serial correlation or autocorrelation, okay, not homoscedasticity. All right, not homoscedasticity, sorry. But then the third point here is that when the error term have equal variances, that is what we call homoscedasticity, okay? Then finally, the mean of the dependent variable for all specified values of the independent variable can be connected by a straight line called the population regression model. All right, so that issue is what has been depicted in this graph. Okay, that issue is what has been depicted in this graph. Now, let's go into detail the meaning of the b test in the regression equation. One of the b tests we see in the regression equation is the slope. All right, the slope beta 1, which is the slope of the regression equation. And as mentioned, it measures the average change in the value of the dependent variable for each unit change in the independent variable. The slope, or the beta 1, it just shows the changes in the y, or the changes in the dependent variable, as a result of a change in the independent variable. All right. And of course, slopes can be positive. That will make the line positively sloped. It can be 0. That will make the line have no slope, or it can be negative. That will make the regression line negatively sloped. All right. Then the beta, which is the y-intercept, as I mentioned earlier, it is the average value of y when x is 0. So if I put 0 here, when x is 0, it means that y will be equal to beta naught. And this means that beta naught is the average value of y when x is 0. Now remember, I'm using the word average value of y when x is 0, and I'm going to explain into detail as we move along. So if you look at this line, this first plane here, we have y is equal to 450 plus 0x. So that means that the slope is 0. That's why we have a straight line. All right. So that means that the change in y as a result of change in x is 0. All right. Because y is not changing. Y is not changing for all values of x. So changing y as a result of changing x is 0. Okay. Because y is not changing. Now, if you look at this one, the changes in y as a result of changing x is positive, because as x increases, y will also be increasing. So that is why in this equation we have a positive slope over here. Then we have 250 to be the y-intercept here. All right, we have the 250 to be the y-intercept. Remember, we are working with data on number of years a sales representative have worked with a company, and then the sales the person is able to make. All right. So what is the method of deducing the regression equation? What method do we go to deduce the regression equation? Now, one of the things I must let you know is that when we have a set of values, okay, for instance, when we have a set of values, so let's use these values as an example. When we have a set of values here, and then let's assume that when we compute the regression equation, we had y is equal to, let's say, 1 plus or 1 minus 2x, okay? So it means that when x is 1, it will be y is equal to 1 minus 2 into bracket 1. That will be negative 1, all right? When x is 2, y will be equal to 1 minus 2 into bracket 2. That will be negative 3. When x is 3, you have y into bracket, y is equal to 1 minus 2 into bracket 3. So 1 minus 6 is negative 5. Okay. So we will have when x is 4, that will be 1 minus 2 into bracket 4. That will be negative 7. Okay. So I think when x is 1, okay, there's even no 1. So when x is 2, y is negative 3 per this function. When x is 2, y will be negative 3. So this is predicted y. Okay, so we have negative 3. When x is 4, y will be negative 7. All right. When x is 6, y will be 1 minus 2 into bracket 6. So that will be 1 minus 12, that will be negative 11. So when x is 8, y will be equal to 1 minus 2 times 8. That'll be negative 15. And I believe this will be negative 19. All right, this will be negative 19. So this is the predicted y. Okay, this is predicted y. So you can see that although these two sets of figures, if we use the regression equation or the regression formula, which I'll talk about soon, to do the equation, we have, assuming we had this equation, okay, assuming we had this equation, what it simply means is that, the actual y here is different from predicted y, okay? The actual y here is different from predicted y. Remember, for now, I'm using a hypothetical situation. This may not be the regression equation for these two sets of data, but I'm just assuming that if it was so, all right? I'm just assuming if that is the case. So this will be the predicted y, okay? So then if you want to look at the deviation of predicted y from the actual y, to be y minus predicted y, so the deviations will be 5 minus 3, that will be 2. No, that will be 8. 4 minus 7 is 11. 3 minus 11 is 14. And this is 17. And this will be 20. All right, so y minus y cap. Okay. Now, these figures here, 8, 11, 14, 17, and 20, it shows the residual or the deviation of the predicted y from the actual y. Okay. Now, let's come back to our slides. So here, the idea is that least square should be, the method for computing the regression equation, okay, should be that the final answer for the regression equation should minimize this residual. Remember, the smaller the residual, the smaller the difference between actual y and predicted y. Let me take it again. The smaller the residual, the smaller the difference between actual y and predicted y. That means that your regression equation is quite good, because the predicted y that we got from the regression equation is very close to the actual y. All right. So in finding the regression equation, we use a method that minimizes the residual errors. All right. And sometimes, because if you remember when I was teaching you standard deviation, or when I was teaching you deviations, sometimes the deviations would add and subtract and you get 0. So sometimes statisticians believe that this residual, we must square it. All right, we must square this residual so that it will remove any negatives and positives, which can end up canceling for the residual to be 0. So when you square the residual, it now becomes square residual. All right, squared residual. Now, the least square method is actually called least square residual method. That's the full name. The least square method is called least square residual method. And that method enables us to minimize the square residuals so that we can get a perfect regression equation. So whenever you hear I'm using least square method regression, it actually means that that method minimizes the difference between actual y and predicted y. Okay. So let's look at this equation. So in this equation, we have a straight line here, and the regression equation for this straight line is 150 plus 60x. Okay, there's the regression equation. Now, when x is 4, okay, when x is 4, the actual value for y is 300, or let's say 312, I believe. It's a little above 300, so it's 312. When x is 4, the actual value for y is 312, okay? But then, if we put 4 in the regression equation, so let's assume that we had a set of data, let's say x and y, and then when x is 4, y is 312, okay? But we have other figures. So once we use these other figures to compute the regression equation, let's assume that we had this regression equation. So when I put x is equal to 4 in this regression equation, I'll get predicted y, okay? I'll get predicted y. And here, what you must know is that the residual then will be the predicted y, which is 390, minus the actual y, which is 312, all right? So 390 minus 312, that will be minus 68, I believe. Okay. Yeah, so residual is basically the difference between actual y and predicted y. Now, what is the method of minimizing the least square residuals? That method is called the least square equation. All right, so in statistics, we will not want to bother you with how to derive the least square equations. All right, I also have a series of videos on econometrics. So that is where I would prove to you how we deduce this least square equation, right? But at this level, we should not be concerned with deducing the least square equation, just know how to use it, all right? And the least square equation, the beta 1 is equal to n sigma x y minus sigma x sigma y all over n sigma x squared minus sigma x all squared. That is how we get the beta 1, okay? And then the beta naught is the mean of y minus beta 1, the mean of x, okay? The mean of x. So I believe most of us are familiar with this particular formula. But this particular formula, if you divide through by n, it's going to get you this formula, because if I divide this one by n, I'll get this. If I divide this by n, this will be the situation here. If I divide this by n, I'll get this. And if I divide this by n, I'll get this. So this formula can be written as this, or we can rewrite the formula in deviation form, all right? So where we have the beta 1 is equal to x minus the mean of x, bracket close, y minus the mean of y, sigma, and then we have sigma xi minus the mean of x squared. This is in deviation form, and you are going to get the same answer, all right? You're going to get the same answer. So here, what I want you to know is that if we have a set of figures, say a set of x figures and a set of y figures, okay? There are a lot of figures for x and y. Now, how come we are able to deduce a single regression equation for all these set of figures? How can we be able to deduce a single regression equation for all these set of figures? The answer is simple. The answer is that the regression equation is estimated using average of all the x and average of all the y. So we estimate the regression equation using the average of all the x and the average of all the y. That is why whenever you see a regression equation like this, it has been estimated at average of x and average of y, because we have a whole lot of x values and y values used to reduce this equation. So it means that this equation is estimated using the average of x and average of y for all the set of x and y values. That is why I said that regression is normally estimated at the mean or the average of the figures. So this is a regression output, which I will explain further in my tutorial video. All right, so we talk about it in the tutorial video. Now, let's talk about the errors. Up until now, I believe I've been able to introduce you to the residual error. where I say residual error is summation of all the actual y's minus their respective predicted y. Okay, this is the sum of residual, okay? But I said sometimes deviations, okay, raw deviations may have a negative and positive canceling effect, okay? So sometimes we want to put them into a standard form before we I mean, when we subtract, sorry, we may want to put them in a standardized form. That is when we may want to square all the deviations. So when you square it, it now becomes sigma y minus predicted y squared. And this is called sum of squared residual error. Okay, sum of squared residual error. Sum of squared residual error. Okay, because here it is sum of residuals. But when you square it, it now becomes sum of squared residuals. Okay, when you square the figure, it now becomes sum of squared residual. Now, another error I would like to talk about is sum of squared regression. Sum of squared regression. Another error I would like to talk about is sum of squared regression. Remember, I've spoken about sum of squared error. Okay, sum of squared residual error. So I'm now going to talk about sum of squared regression error. Sum of squared regression error. Now, remember that regression is normally estimated at the mean. Okay, I mentioned it earlier. So regression is normally, it will be estimated at the mean of x and mean of y. So whenever you have mean of x and mean of y, when you plot that figure, okay, and you have your intercepts, you can just draw the line through. It will give you your regression equation. Whenever you have the mean of x and have the mean of y, and you have your intercepts, when you draw the line through it, you get your whole regression equation. That is why we say the regression equation is estimated at the means, all right? The regression equation is estimated at the mean. Now, if I have this regression equation and I put in an x value, okay? When I put in an x value, let's say the mean of x was, let's say 10, okay? And the mean of y is, let's say 20, that is there. So let's say I'm putting in an actual x, not the mean of x. I'm putting an actual x, which is equal to 20, okay? When I trace it to the regression line, I'll get a predicted y, which is also here, all right? So you then see that when I put in an actual x of 20, because this actual x is not the mean of x, when I put it in the regression equation, the predicted y I'll get is not the mean of y, okay? Because I only get the mean of y when I put in the mean of x, because regression equation is estimated at the means. But once I put in an actual value of x, which is not the mean of x, when I put it in, I'll not get the mean of y, all right? So then the difference between predicted y and this mean of y is called sum of squared regression, all right? So predicted y minus the mean of y, of course, when we square it and we find the summation, is called sum of squared regression, all right? And the explanation to sum of squared regression is the error or the deviations. The sum of squared regression is the error or the deviations that can be explained by the regression line, all right? It is the error or the deviation that is caused or that can be explained by the regression equation or the regression line, all right? Now, another thing we can also see is that apart from the mean of y and then the predicted y, we can also have an actual y at this value of x. We can also have an actual y at this value of x. Now, the actual y at this value of x is not explained by the regression equation, all right? It is just in the raw figures which is given to you in the question. So the relationship between actual y and then actual x is not explained by the regression equation, all right? So here, that means that the difference between the actual y and the predicted y, as I mentioned earlier, it is called sum of squared residual error, okay? Or it is the error that is not explained by the regression equation. It is an error that is not explained. It is an error, okay, or it is a deviation that is not really explained by the regression equation, unlike the deviation between y cap and y, which is explained by the regression equation. Okay, so now we have two errors. We have sum of square residual error, which I want to call it sum of square error. Okay, sum of squared residual error, which I want to call it sum of squared error. Then we also have the sum of squared regression. Okay, when you add these two, it now becomes sum of squared total error. When you add sum of squared residual error, the sum of squared error, to sum of squared regression, it now becomes sum of squared total. Okay, sum of squared total, or total sum of squared. All right. Now, if I take the sum of squared regression divided by the total, so if I make a sum of squared regression over sum of squared total, what I'm eventually saying is that, remember, errors are variations or deviations. Errors. The errors are variations or deviations from the actual. So error is a deviation or a variation. All right. Now remember, this is the total variation. If errors are variation, it means that sum of squared total is the total variation. Okay. Then sum of square regression is the part of the variation of the total variation that can be explained by the regression equation. Sum of square regression is the part of the total variation that can be explained by the regression equation. So in other words, if I take it as a percentage of this, it is called R squared. Okay. It is called R squared. The percentage of total variation in Y that can be explained by the regression equation. The percentage of total variation in Y that can be explained by the regression equation. All right. That is the R squared. Okay. So here we have R squared to be sum of square regression divided by sum of square total. All right. And because it's a percentage, definitely it must be between 0% and 100%. So in terms of decimal, it must be between 0 and 1. It cannot be more than 1, and it cannot be less than 0. All right. Okay. Now let's get into the hypothesis testing bits. Remember, we can have an R squared, or we can have a coefficient. The another name for R squared is coefficient of determination. All right. Another name for R squared is coefficient of determination. And I've said that by definition, R squared is the portion of the total variation in the dependent variable that is explained by its relationship with the independent. Or in other words, that is explained by the regression equation, in other words, or in simple terms. Okay, the proportion or the portion of total variation in the dependent variable that is explained by the regression equation in simple terms. Okay, now if I pick a sample data and I get an R squared, it does not mean the R squared is significant, or it does not mean the R squared will apply to the entire population. It doesn't mean that. Okay, because if I pick a sample data, like the same way I explained in correlation, the fact that you've gotten correlation for sample data doesn't mean it will apply or it will be significant to the entire population. All right. So here also we need to test whether the R square is also significant, or whether the R square for the sample will apply to the population. So the default null hypothesis is that the R squared is not significant, or the R squared is equal to 0. That's the default null hypothesis. And the alternative is that the R squared is greater than 0. As I said, R squared cannot be negative. That is why we don't make it not equal to 0. Okay, we make it greater than 0 because R squared cannot be negative. Now, the new thing we are going to learn here is that when you are testing significance of R squared, we don't use the T value or the P, we don't use the T value or the Z value. We use the F value, the F statistics. So if you are testing significance of R squared, it is not T statistic. We use the F statistic, all right? And this is how we compute the F statistic. It is the sum of square regression divided by 1 all over sum of squared error divided by n minus 2. And that is how we find it, okay? So if you are testing at 95% confidence, you just go and read the required confidence level, and you read the degree of freedom as depicted in this slide. You read this degree of freedom, okay? You read the degree of you read this degree of freedom from the table, and you're going to get the critical F. All right. And once you get your critical F, you now compute this F here. And once you compute and it lies outside the bounds of the critical F, you reject the hypothesis as usual. But when it lies within the bounds of your critical F, you are not going to reject the hypothesis, okay? But for simplicity's sake, normally in examinable situations, you may not be asked to compute the F statistic. The F statistics would be estimated for you, or sometimes the p-value, all right, the p-value of the F statistic will be computed for you. And once that p-value, obviously when it is less than 0.05, it means that you reject the null hypothesis that the F stat, the R square is not significant, and conclude that the R square is significant, all right? So sometimes p-values will be estimated for you to conclude with the F statistic. That's a very simple way. Now, that means that if your p-value of the F statistic is greater than 0.05, it means that we will fail to reject this null hypothesis, and our conclusion will be that it is not significant. The R square is not significant, okay? Now, moving forward, we can also test the significance of the slope. We have y is equal to beta naught plus beta 1x. So we can also test the significance of this slope, all right, the slope, or the beta coefficient. Now, the default null hypothesis is that the beta coefficient is equal to 0, all right? The beta coefficient is equal to 0. That is the default null hypothesis. Then, because beta can assume a negative or a positive figure, the alternative is that the beta or the slope is not equal to 0. All right, the beta or the slope is not equal to 0. Okay, so we can also test the significance of this beta. Of course, when you use the formula to compute the regression equation, the beta you've gotten is for the sample. So you want to check whether the beta that you've gotten for the sample is also significant for the population. And that is the whole essence of hypothesis testing. The essence of hypothesis testing is to test whether something that is true for the sample is also true for the entire population. All right. So how do we compute the test statistic for this hypothesis? Now, the test statistic for this hypothesis is the estimated beta minus the hypothesized beta all over standard error of the estimated beta. So when you use your formula, the regression formula, okay, to get your beta, that will be the estimated beta. All right, that will be the estimated beta. Then the hypothesized beta is that in our hypothesis, the beta is equal to 0. So in other words, we will have T is equal to beta 1 minus 0 because the hypothesized beta is 0 all over the standard error of the beta. All right. Now, how do we get the standard error of this beta? Okay. If we have the entire population, the standard error of the beta will be the standard deviation of the error term divided by square root of xi, a sigma, or summation of the x values minus the mean squared. All right, all of them, everything here square roots. Okay. Now, don't worry yourself about these computations because at the statistics level, the emphasis is on your interpretation. So probably all these things are usually computed for you in a standard statistic test, right? Obviously, when we don't have the population, we are using the sample we use the sample standard deviation of the error term, all right? Divided by the square root of summation of sigma xi minus the mean of x squared, all right? So you don't have the population standard deviation of the error term, we use the sample standard deviation of the error term. And I said the standard error of the beta, this formula, this whole formula, usually the standard error of the beta is computed for you, all right? So all that I want you to know here is that the t-value of beta is gotten by dividing the coefficient or the estimated beta by the standard error, okay? The coefficient or the estimated beta by the standard error, you get the t-values, all right? You get the t-values. That means that if t is equal to estimated beta over standard error of the beta, change of subject means that the estimated beta 2 is equal to t times standard error of the estimated beta. And again, if you do change of subject again, it means that standard error of the estimated beta is also equal to the estimated beta over t, all right? You do another change of subject. And some of these concepts can be tested in a standard statistical test. Now, let's look at an example here. So in this example, let's assume we are testing at 5% significance level, which is 95% confidence interval. And because the hypothesis is equal to and then not equal to, it makes it two-tailed, all right? It makes it two-tailed. Now, let's also assume that the sample size is 12, and the degree of freedom for regression also is n minus 2. So the degree of freedom will be 12 minus 2, which makes the degree of freedom 10, okay? So when you read degree of freedom of 10 against 95% confidence level, two-tailed, okay? Two-tailed, 95% confidence level, when you read it, all right, when you read two-tailed 95% confidence level at the degree of freedom of 10 from your statistical tables, you get the critical t-value to be 2.228, okay? 2.228, and because it is two-tailed, here will be negative 2.228, and here, sorry, here will be positive 2.228, and here will be negative 2.228, all right? So let's compute our t. So the estimated beta was 49.91. The hypothesized beta is always 0. And then the standard error is 10.5. So when you fix them in the t formula, the computed t is 4.752. The computed t is 4.752. And it will lie, so this is the acceptance region. So the 4.752 will lie outside the acceptance region. That means that we will reject the null hypothesis that the beta is not significant. And we will conclude that the beta is significant, okay? And then we will conclude that the beta is significant, or a linear relationship exists, all right? That's how we also do hypothesis testing for the slope or the beta. So these are the steps. These are the steps in simple linear regression. We define the independent and the dependent variables. We develop a scatter diagram. We compute the correlation coefficient if it's necessary. We calculate the least square regression and obtain the R square. We conduct a test to determine whether the regression model is statistically significant. So to check whether the entire model is significant, we use the R square, because R square shows the percentage variation in the dependent variable. That can be explained by the variation in all the independent variables. So once your R square is not significant, it means all your independent variables put together cannot explain the dependent. That means that on the overall, your model is not significant, right? Then afterwards, we reach a decision and then draw a conclusion, okay? Now, there are several uses of regression equation. We can use it to estimate a lot of things. So let's assume that there's a regression equation here. So the interpretation of this regression equation here is that when x is 0, average y will be 31.1658. When x is 0, it means average y will be 31.1658. That is how we interpret this slope, all right? And if you want to interpret the, sorry, this how we interpret the intercept, this is the intercept. And if you want to interpret the slope, it is the change in y as a result of change in x. So then the interpretation of this figure here is that a unit increase in x will lead to a 0.0286 unit decrease in y. A unit increase in x will lead to a 0.0286 unit decrease in y, holding all other factors constant. So that is how we are going to interpret this slope. And assuming this is the R square, okay, the R square is the percentage variation in y that can be explained by the variation in all the independent variables. Okay, so here normally we wish that you compute it in percentage form. So if you are given a question, they give you R square in decimal and they say still compute the R square. What they require is that they just want you to multiply it by 100 and get it in percentage form. So the R square, it will be 30.16%. And the interpretation is that 30.16% variation in the dependent variable can be explained by the variation in the independent variables, all right? 30.16% variation in the dependent variable can be explained by the variation in the independent variables, okay? Now, aside using t value to check, we can also use p value to assess the significance of the beta or the slope, all right? So when we are using p value, remember that when your p value is less than your critical value, so if you are testing at 5%, your critical value will be 0.05. So when your p value is less than your critical value, we reject the null hypothesis. And when your p value is more than the critical value, we accept the null hypothesis. All right. So for your model to be, for the beta to be significant, we always wish that the p value will be less than 0.05 so that we can reject the null hypothesis of insignificance and conclude that the beta is significant, right? Now, also remember that anything that has a t value or a z value, that thing too, we can compute a confidence interval for it. Because actually confidence intervals are constructed using point estimate plus or minus the critical value times the standard error. So once we have a t as a critical value, it means that we can compute the confidence interval. The confidence interval for the slope is beta plus or minus the t statistics times the sample standard error. So here, the t statistics times the standard error of the beta, right? So the point estimate is the beta plus or minus the t times standard error of beta. It can help us construct the confidence interval for the regression slope, all right? And we can do it at 95% confidence, 90%, or even 99% confidence. Then depending on the confidence level, it will help us choose the t that will be used in constructing the confidence interval. So note that we can also construct a confidence interval for the slope. So there's the steps. All right, define the dependent and independent variable, obtain the sample data, compute the regression equation and the standard error, construct and interpret the confidence interval for the regression slope. All right, so confidence interval has been taught extensively. All right, so the only new thing here you have to learn is how to compute the standard error of the beta. All right, but as I said, it may not be necessary because usually it is given to you in an estimated output. Okay. All right. So here, there's a question, and the standard error of the slope has been given as this, and the estimated slope has been given as this. So if you are testing at 95% confidence, the critical T here is 1.97. The critical T here is 1.97, and we have the standard error to be this. So it is the point estimate, which is 75.70 plus or minus the critical T times the standard error. So once you compute it, it will give you a confidence interval of figures from 68.25 to 83.15. So because we are testing at 95% confidence, we can say that we are 95% confident that the true population slope will lie between 68.25 and 83.15, right? So that is how we interpret this confidence interval. Okay, so that's the confidence interval for the slope. And we can also have the confidence interval for the mean of y given x. So those things two are there, and that is that. Now, what are the common problems in this topic? Now, regression is the most widely used statistical tool. That is why I said this topic is very important. In research, the mostly used statistical tool is regression. Even though we have one sample t-test, paired t-test, etc., we have correlation. One of the most commonly used is regression. Number two, the conclusion and inferences made from a regression line are statistically valid only over a range of data contained in the sample. Again, never assume correlation is regression, because correlation does not imply causation. Then again, a high coefficient of determination or a high R-square does not mean that your model is good. Of course, if the R-square is big, it's good because it means that a higher percentage of the dependent variable can be explained by the independent variables. But, well, it does not mean so. Because sometimes maybe you are putting in some figures that's making the R-square very big. That does not mean the figures are really good, all right? That is why sometimes in regression output, you see adjusted R-square, okay, which adjusts for any unnecessary noise in the R-square. So most of the times, for research purposes, people normally use adjusted R-square, not the R-square itself, for research purposes, all right, because it controls for any unnecessary noise in the R-square. Then finally, confidence prediction and errors may simply be too wide for the model to be used in many situations. So in summary, we've talked about regression, and we talked about R-square, and we said to check the significance of R-square, we have to use the F statistics or the ANOVA table. The F statistics or the ANOVA table is used to check the significance of the R-square, or in other words, it's used to check the significance of the entire model. Then we also came to the T statistics to check the significance of the B test, all right? Where we said when the computed T is more than the critical T, we reject the null hypothesis, all right? Now, for simplicity's sake, statisticians say that when you are working with large volumes of data, you may not be able to read the observed, the critical T from the T table, because the T table has a limit. So once you are working with a very large data, the default critical T for 5% level is 1.98 or 2, all right? The default critical T when you are working with large level of data, which cannot be read from the T table, is 1.98 or 2. That is why we say that when the T value is more than 2, we reject the null hypothesis and say the model is what? Significant. All right, so this will bring us to the end of the series on my statistics videos, particularly regression. And if you want more understanding, let's meet in the tutorial section on my tutorial video set. All right, I would like you to comment, share, most importantly, subscribe to this channel, and let's have your feedback. Thank you.